What is up, fellas? Welcome back to my channel. This is Tony, aka One Lead Code One Day. If you're new here, this channel will do one lead code per day, following the pattern of topics or series. Basically, I'm going to be studying with you together on a lead code problem I have never attempted before. You heard that right, there is no prescripted answer. We're on the same page here. But don't you worry, I got your back and I promise that I will submit at least an average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background, so I'm no better off than most of, if not all of you guys, in terms of coding knowledge. But that is okay. It is all about learning on the go. You can think of this video as a first-person gameplay of cracking lead codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's code problem. Today, we continue on Series 1, Everything About Dynamic Programming, and today's problem is Number 740, delete and learn. So let's get into it. All right, delete and learn. Medium problem. You are given an integer array nums. You want to maximize the number of points you get by performing the following operation any number of times. That is, pick any nums I and delete it to earn nums I points. Okay, pick and delete. So it's like popping something out of the array. Afterwards, you must delete every element equal to nums I minus 1 and every element equal to nums I plus 1. Basically, you must delete every element small, no, one less or one larger than the one you picked and deleted. Okay, so it's like a collateral uh, damage or collateral deletion. Return the maximum number of points you can earn by applying the above operation some number of times. This is really an interesting problem. You see, it's almost like a grenade if you think about it. You you pick something, uh, the grenade explodes and it causes some collateral damage. Or you can think of it like a fruit picking task. If you pick the middle fruit, you're going to ruin the fruit on the left and on the right because your machine or your picking tool is not precise enough. It's always going to damage something. Yeah, it's like a corn, right? If you want to pick, you know, one corn, one grain of corn out of like a corn bar, like a bar of corn, um, you will always end up damaging, the nearby corn grains. So that is what this problem is. Uh, well, when we say nearby, yeah, so when we say nearby, it means, spatially nearby. Is that correct? Let's see, output is 6. Let's take a look at the explanation. You can perform the following operation: delete 4 to earn 4 points. Um, Consequently, 3 is also deleted. Oh, okay. I see. So I was wrong. It was not like a, it was not like a collateral deletion of spatially adjacent numbers, but value-wise adjacent numbers. So if you delete 4, if you take 4 and you take that reward, you're gonna have to delete 3 and 5, wherever threes and fives are in the array. So really, there's like an inherent uh, list of number ranked by their value, you know, and then yeah, you can build maybe a dictionary, just finding out where those numbers are, and then decide which one you're gonna pick first and which one you're gonna ditch first. Um, right. So that's the one intuition that we can follow, but maybe it's not the best. So be very careful trying to generalize the rules because the way you generalize the rules is going to affect how you code. And if you make a crappy generalization in the beginning, it's going to only make your life much, much harder later. Okay, so let's not jump into conclusions on what to do. Let's take another look at the second example. Input nums equals to 2, 2, 3, 3, 3, 4. Okay. Uh, so we have more numbers, and then they're like 2, 3, 4 again. But you now just have three threes and two twos. So if you, for example, if you take 2, then you're gonna have to delete all the three threes, which is a pretty big loss of numbers, right? But anyway, you can only take 1, 2, or like 1, 3 because all the values. Oh wait, actually you can take threes multiple times because it won't delete itself elsewhere. It will only delete its adjacent values elsewhere. Yeah. So actually, if you have like three threes, you just take three threes, all of them, and you automatically have to delete 2 and 4, but that's fine. You only deleted 9. So you only deleted like a total value of 8, but you still kept 9. You still get to keep 9, so that's good. Right, right. So it seems like, the takeaway from the second example is that you want to keep like you want to pick a number that is repeated uh, the most often because those won't disappear ever. Like you can just keep exploiting that number until you picked um, all instances of that number. But this is like not very generalizable, right? So um, and at this point, we're still not sure how to form a dynamic programming formulation of the problem. It's all pretty random right now. Like right? We need to, abstract this thing into a actionable rule for programming. Now, what we see is that you have, these numbers that's scattered all around in the list, and then you want to find a way to um, optimize the picking process. Picking one number is going to cause uh, the adjacent values, the adjacent number values to vanish. Uh, so does it really matter like spatially where they are? No, it doesn't. I mean, you can relist them. You can relist them in like an ascending or descending order because I think that doesn't really hurt, doesn't really reduce any information. That doesn't really reduce any information in the list. So the first thing you want to perform, it doesn't hurt, is to um, sort the list into an ascending or descending list, or put like bins. Yeah, or you can make dictionaries where the key, um, is uh, the key is like the number itself, and then the value is like the how many occurrences it has. Or because now actually the order matters, and dictionaries doesn't really have sorted orders for the keys. Mm, or does it? Like we cannot use integers for keys, but maybe we can use the string version of the integer for keys, but then the ranking is all gonna mess up. All right, so we're not doing that. We're gonna do like two lists. Maybe one list to remember the value, to remember the integer itself, and then the second list to remember the occurrence of the value. And we make sure that, uh, um, we make sure that, the list is kind of like sorted because uh, we want to know if there are like adjacent values, right? Right, right. But is that really going to help? Like sorting things? This questions me again because anytime when you take a value, decide to take an integer, it only affects its adjacent values, right? When I say its adjacent values, I mean if you take 9, it's only going to affect 8 and 10, right? It's not going to affect, 5 or 6 or 7. So in a way, it only has like a local impact. So maybe you don't need like a long chain of resorted lists because sorting the list is going to cost you some computation, and for Leetcode, it's all about efficiency. So maybe a dictionary is not such a bad idea, and we can just basically transform this list into a dictionary by popping all the values into dictionaries, and then once we finish that popping process, which takes computation of O(n), because popping all the values would require n operations. Once we've computed that, and then we're gonna store, a dictionary with each integer and its corresponding occurrences. Then we can start to, I guess, start to make a strategy on which values uh, to pop out, right? To pop, to take, and then see if we need to pop out anything. One such operation, like working on any value, well, there's like a bisection of choices. You either take one value or you don't take one value, and the resulting action of taking one value would automatically eliminate potentially the adjacent integers in your dictionary, and you're just gonna pop them out in the dictionary, and you're gonna get your value um, of total reward by pop by exhausting the dictionary, right? Yeah. Um, but I still don't see how a dynamic programming structure can come out of it. This is still something. This is still something I think beyond my thinking. So so let's actually try to uh, write something down here. So this is 740. Delete and learn, delete and earn, right? And the question that we want to be asking ourselves, to kind of coming up with the generalization is the question is going to be uh, how can we reuse computation? How can we reuse computation in the process, right? Because reusing computation is the essence in dynamic programming because we want to rely on um, small pieces, excuse me, small pieces of computation to build up all the way um, you know the, the the total computation or the full computation, and that is our idea. So how do we do that, right? How do we do that? This is something we're about to work out and find out. Yeah. All right, we got back from a bathroom break. Now let's get back to this um, reuse computation thinking. So in my opinion, in order to use dynamic programming, you need to have these sub problems uh, on which you can simplify the solution of more complex and more complete um, mega problems, right? So you want to have these sub problems that you can solve. Let's just draw some very simple examples. See how this may work. Um, let's use black, right? For example, let's say we have an array of 1, 1, 2, 3, 4, 4, 5. Okay, not a lot, but it's something. Now, um, because I think the the place they appear in the array in the list doesn't really matter unless you want to you know use this as your sub problem, like spatially take out the first number and use this as your sub problem. That's not a good choice because you know by the problem dynamic, if you take out number one, you automatically, well, if you pick, let's say if you pick number one, you automatically eliminate number two as well. So you can't just say we're gonna keep um, we're gonna take the first one and keep the rest of it as a sub problem. That doesn't work. So the better way to represent this, I think, is to actually store this to reform this um, into a dictionary where the keys are the integers, or I mean the string version of the integers, and then the values are the occurrences, like the frequency in which they appear. So it's gonna be like an become a dictionary, and then we're gonna have one, which appears twice, and we'll have two, which appears once, and we'll have three, which also appears just once, and we'll have four, which appears twice, and lastly we'll have a five that appears once. So this is our new representation of the problem. It's more compact uh, and it's more useful. So now I think we can apply that subproblem logic here. So let's say we want to take something and the remainder of after that action is a subproblem, right? That's generally the dynamic programming logic that you take some action and you land at some other state. Um, in this case, whatever is left over, and then that leftover part is going to be your subproblem. That's how we are trying to come up with something that we can reuse. Right, so let's say if we take the first value, 1, what that'll do is that it's going to eliminate 2 because it's an adjacent value. So what we're left with is this remaining part of it. And this will become uh, our sub problem that we're going to solve. Of course, we're going to need to add the reward for this step onto this as well, but this is going to be our sub problem. And then for this sub problem, for example, we can again take number 3 and it will automatically eliminate number 4. And that will leave us with this subproblem with just one value, one integer 5 with one occurrence in there. So yeah, I think that is it. Um, how do we write this in a recursive way? Let's um, let's call our dictionary, original dictionary D, right? And then of course this is nums. This is what is given in the problem. And we create this dictionary, call it D. And the total reward, or the maximum reward, is going to be, let's say, we need to we need to you know use something as a right. So how do we call this? D something like D0, or what is it? Um, okay, let's just call it D0 for now. Um, so D0, meaning that we didn't take anything out, is going to be right. The general DP expression always has a max, and uh, you can write it as a maximum between two values, meaning two actions taken at the first step. So the first step we can either pick the first key value, or we can skip the first key value. So yeah, so if we skip it, what does it mean by saying if we skip it, right? That is kind of like weird. If we skip it, what do we mean if we skip it? Right. For one value, the complete decomposition is like you either sacrifice it or you you take it. Yeah. So there's like this bisection here, or for each value you either take, or or you delete it. Uh, and by delete it we mean the only way you delete it is if you take its adjacent integer value, if it exists. So this may be a possibility, but maybe it's impossible if it doesn't have any, adjacent values. Then there's no way you can delete it, right? So take it or delete it. You can either take number one, or you can delete number one by taking number two. Or if there's no number two at all, then you don't have an option to delete it at all. You just have to take it. Uh, right. But in principle, we still have this bisection. Um, so we either take it or we delete it. Right. So let's say the first one is we take it. We take number one. So that is the reward of taking number one. Okay. Taking number one. And what is the remaining subproblem? The remaining subproblem becomes that of the, you know, you took it, so you're gonna have to delete uh, um, the neighbors of one. So you delete 0 or 2 and 2, all the zeros and twos. Uh, so what exactly is that? Uh, it'll become, right, so how do we represent that? Minus 1, minus 2, I guess. Right, so yeah, you basically, took out that, right? Basically took out values 1 and 2. Uh, and then if you don't take number 1, if you don't take the 1 value, you're gonna have to delete it in a way. Uh, what are the ways of deleting it? Well, to delete it, you have to take number 2, or you'd have to take number 0. So this will become taking number 2, right? So again, this becomes two options, right? You either take number 2 and then um, if you take number 2, then your remainder becomes um, you have to delete 1, 2, 3, right? You have to delete all these integers from the right from the dictionary, right? Uh, can you take? Is there any other way to take out number 1? Well, if you take if you take a to delete number 1, well, if you allow us to take the value 0, then we can delete the number 1. But does it allow us to do so? Uh, okay, so the minimum of any element in that nums list is 1. So 1 is really the smallest, and then we can go up to 10,000. Okay, and the length can go really high. Okay, um, that means this is the complete expression uh, for I guess the reward, right? Like yeah, the reward. So maybe we should write, instead of writing D, we should write reward, because D means actually the dictionary, but R is a reward function. Uh, so here, R12, it means the maximum reward after removing the value 1 and 2 from the dictionary, right? And then R123 means the maximum reward after removing 1, 2, and 3 from the dictionary, right? But this is kind of like a special case. And also, because we're starting on number 1, um, this is like the total R, right? We can we can also start on some other value. Let's just be more general and start on some other value here. So if we don't focus on the first element, but just focus on actually some element in the middle, let's say if we focus on number 3 right here. So alternatively, this R expression can be written as uh, choice number 1 is we take number 3. So we take out number 3 and get all the reward for number 3. And then we're going to have to deal with the remaining sub-problem, which is, we have to remove 2, 3, and 4 from the dictionary. Or if we don't take number 3, how about that? If we don't take number 3, what does that mean? Um, it means if we don't take number 3, uh, or like if that means if we delete number 3, uh, so number 3 is either taken or deleted, right? In the end, every value is either taken or deleted. So if number 3 is deleted, it has to be because a neighbor of 3 was taken. So it's either number 2 was taken or number 4 was taken. So there are two cases, right? So let's say the first one is um, number 2 was taken. And and if number 2 was taken, then the remaining subproblem would be uh, taking out 1, 2, and 3 from the dictionary. But there's the remaining choice of number 4 taken. So if number 4 was taken instead, then we have the remaining problem of taking out 3, 4, and 5 from the dictionary. So here we actually land at this equation. Is it complete? Um, let's take it slow because this is something you really want to be slow and thinking thoroughly about. So we're saying that, right, so we're saying that if we focus on 3, focus on the number 3 first, this is focus on number 1 first, this is focus on number 3 first, right? If we focus on number 3 first, we separate the cases into 2 general categories. Category number 1 is this, where you take the value all integer 3's, and then you have to deal with the remaining subproblem after removing all the 2's, all the 3's, and all the 4's in the dictionary, or like equivalently in the original nums list. And the other case is actually for when you delete, yeah, when you when you delete 3. So there are 2 sub cases for that. So this case is delete 3, and there are 2 possible ways to delete 3. One is to take 2, and one is to take 4. So and these 2, take 3 or delete 3, this makes a complete decomposition of you know all the possibilities for a first step. You know, for any action, it's either take 3 or delete 3, or actually leave 3 alone, right? But I mean, if we force ourselves to act on 3 first, which is fine because I think the order of taking things don't matter. I could be wrong, but I think the order of taking values uh, don't matter. Uh, because if it does matter, we're screwed. Then this is not right. So let's, uh, assume, this could be a bad assumption though. Let's assume the order doesn't matter. The take order does not matter. Does not matter. And this is an important assumption that we're making here. We're not sure if it's going to hold, but we just take the assumption here. If that assumption holds, then the taken order doesn't matter. So we can take number 3 first, or delete number 3 first, and basically we will have a recursive relationship. Um, but this is looking not very elegant because compared to previous dynamic programming recursive relations where you only have what 2 of those cases in the max function bracket, now you have 3. Now you have 3, and um, and we don't seem to be able to, further abstract this uh, into something. Okay, yeah, and I start to have a feeling that, if we generalize this way, we can end up with a super messy recursive relationship that we will never be able to get right in terms of coding. Yes, I do have this fear now. So what should I do? I should sit back and I should rethink about this and think whether this is actually a good idea or not. Right, we do have subproblems here, and we definitely could reduce these subproblems into even smaller subproblems. Um, right? Yeah. So, um, but because it's like kind of like a dictionary, um, so yeah, in a way we have to store dictionaries. And you can see that, this R234, R123, and R345, those are three different values. And, when we go down, um, we might need to store a lot more different R values. So on the space complexity side, this algorithm may suck. So maybe I don't know if transforming the nums array into a dictionary is a good idea or not. I mean, it's good in the sense that it kind of like uh, simplified and reduced the total number of elements because now we can basically group uh, the same values into kind of like key value pairs. That's a good thing about dictionaries. Uh, and of course, this transformation alone, it will take a O of n computation and O of n storage in turn. Um, and that is even before we perform any of these dynamic programming computations. So I am thinking whether it's possible to skip this transformation step. Yeah, skip this transformation step, and uh, maybe we could just rely on using the original nums list to build subproblems. Right. Let's give that a thought because I think down this line it doesn't really look very promising. So let's switch strategy. I'm going to see if I can use a different color. And by using a different color, I may really mean using a different strategy here. Yeah, using a different strategy here. So I'm thinking about, let's see, let's revisit, let's revisit the nums list. And let's say, what kind of subproblems can we create by taking some action on this list? So for example, let's again work on the action of taking number 3. What that does is that it will effectively eliminate number 2, the two number 4s, and we're left with an array of 1, 1, 5. So 1, 1, and 5 becomes our subproblem, right? But that is just, one of the possibilities for the first step. What are the other possibilities for the first step? So instead of taking 3, I mean, instead of taking 3, uh, we can leave 3 alone, right? Yeah, we can leave 3 alone. That's um, taking 3 or not taking 3. Right. So the new bisection rule, I guess, is like either take it or not take it. Right. So I think that's a good it's a good intuition. So the new bisection, well, we do bisection because we want to keep our actions at each step on a low level. So either to take a certain X or or not take a certain X instead of like deleting X, because deleting X is like a subset of taking X. I think you can choose to do that, or you can choose to, bisection of action, right? Bisection of action. You can actually do this. So what happens if we just not take the number 3? Let's try this. So nums, again, I'm just writing it up again. 1, 1, 2, 3, 4, 4, 5. If we do not take, if we leave this number 3 alone and we don't take it, um, is this like a sub problem? Well, we still have to take something, right? Yeah, we still have to take something. And how to represent the value of that, like not taking 3? How do we represent the value of not taking 3? Uh, what is certain about not taking 3? Well, the certainty about not taking 3 is that, I mean, if the take order doesn't matter, then in the end, if you, I mean, if you don't take 3x at this first step, you may still take it later, right? It only means that um, yeah, if you don't take it now, you can still take it later. So what it means is that we can take 1, we can take 2, we can take 4, we can take 5. We can still take any of these values. Let's just, uh, represent that subproblem. Um, right. What is the subproblem of like not taking 3 at the first step? Um, it's just really hard for me to think of what that is if we don't take number 3 at the first step. That means we are. Does that mean we're taking number 4? No, we because maybe we will take number 3 at a later stage and it will eliminate number 4 anyway. So if we do not take number 3 in the first step, it doesn't mean that we will not take it later. It only means we'll take something else in the first step. And how do we represent that? The value of that? Uh, it'll probably mean, yeah, it'll probably mean um, taking out everything else in the first step. But that's hard to generalize, right? Like, what does it mean? So I guess I'm again stuck. But what if like we still use the transform? What if we still use the transform, but at this time instead of using the bisection of take and delete, we use the bisection of take or not take in number 3. So for taking number 3, we know that, the maximum reward for taking number 3 in the first step is this. But instead of say delete number 3, what is the combined value of not taking number 3? Uh, if it's like not take number 3, that means You either take 1 or take 2 or take 4 or take 5 uh, in your first step, right? So it'll include take 2, take 4, as well as take 1, take 5. So it will actually make this expression even longer. Is that true? But then which one is right? That is what I am concerned about. Because you don't want to overcalculate uh, or undercalculate. You just want to calculate the exact amount that is required. Um, so this decomposition or bisection of take 3 or delete 3 is one way to categorize it. Another way is to categorize it as either take 3 or not take 3 mm, in one certain step. Right. Uh, Under the assumption that the taking order does not matter, uh, which one is correct? I guess then this one in black is correct because if the take order doesn't matter, then not take X, according to this definition, only meant not taking X at this current step. It doesn't really mean that we're not going to take X later. So there could be cases where, so this kind of differentiation, it could cause problems because even if we do not take X at this current step, later on we may still take X, which again belongs to this category instead of this category. So that will cause like a jump of categories later on. So I think this is not a very good way of doing things. So we're gonna have to stick with this, take or delete. So if it's take or delete, and we're stuck back with this relationship, and I don't really have much confidence in implementing this because first of all, it's long, it's lengthy, and then maybe maybe it's actually wrong. So okay, I think at this point we want to take a peek at the solution and get some inspiration from it on how do we generalize this problem. So this problem seems to be a little bit hard. We're gonna jump directly into our solution and see if we have some approach that is similar to ours but executed more complete. So we have top-down dynamic programming, we have bottom-up dynamic programming, we have space-optimized bottom-up dynamic programming, um, and we have iterate over elements. We have further thoughts, the best of both worlds. So, so dynamic programming, there were three approaches. I think we were kind of like trying maybe the top-down approach. So let's read on. This problem is an excellent example of why it is important to read the problem description carefully. We can make a substantial optimization by noticing that the order of the elements in nums is irrelevant. Right. I think we took that, we understood that. At any operation, we pick a number, let's say x, and delete all occurrences of x minus 1 and x plus 1. That means if x occurs multiple times in nums and we take one, we may as well take all of them because after all, after deleting all x minus 1 and x plus 1, we can only stand to gain more points by taking additional x. Right, we got that point too. Before we start, we can simplify nums by collecting all duplicate numbers together. We got that too because we were thinking of making it into a dictionary, transforming the list into dictionary first. As an example, nums can be represented as a hash map. Okay, so you're thinking of a hash map. I was thinking of a dictionary with numbers as keys, which maps to the numbers of times the keys occurs. In nums, 2, 2, 3, 3, 4 would be converted to 2, 2, 3, 3, 4, 1. That's exactly a dictionary, yeah, or hash map, depending on what language you use. Furthermore, since we're only really concerned about how many points each number can give us, we can multiply the keys and values to represent how many points taking the key will give us. Yes, that is something I was thinking, but I didn't say it explicitly. And that's good, like, multiplying to get, the total number of points you can gain for taking each value. That's smart. I think um, up to this point, we are on the same page. Now we want to know how the solution generalize the recursive relationship. In the first approach of this article, we will talk about an algorithm that solves this problem in detail. In the second approach, we will implement the same algorithm in a slightly more efficient way. Okay. Then we will look at some approaches that build on the idea from the first two approaches, but each one will have differences in their time and space complexities. Okay. That's why we need to read the first one first. Approach 1, top-down dynamic programming. Intuition. There are two characteristics of this problem that hint towards the use of dynamic programming. The first is that the problem is asking us to find the maximum of something. Right. So this is actually good. Like these are telling us what hints to find to suggest towards dynamic programming. The first is that the problem is asking us to find the maximum of something. The second is that we need to make decisions on which numbers to take. And each decision may influence future decisions. Right. For example, if we wanted to take all the fives, then we can no longer take the fours or sixes. It's right. As described in the dynamic programming exploit card, these two characteristics suggest that we should consider a DP solution. If you're new to DP, then reading this card is highly recommended. Let's actually read it and see what that is. Oh, intro. This is like a mini lecture. Common pattern in DP, common patterns continued, more practice problems. This is an interesting course. We'll come back to it later, but we don't have time for this right now. These two characteristics suggest that we should consider DP. Yes. The difficult part about this problem is figuring out how to always make the optimal decisions on which elements to take. Oh, how to always make the optimal decisions on which elements to take. That is a smart move. Like if you can guarantee that each step is an optimal move, uh, then you don't need like the recursive relationship anymore. You just take the optimal action at each step all the way down until you exhaust that hash map or that dictionary, and then you're done, right? Let's look at an example to illustrate the problem. Okay, we have this list of numbers. As we mentioned above, we convert this into a format that's easier to use. So we have a hash map or dictionary. If we tried moving from smaller keys to larger ones in a greedy manner, our first decision would be to take all three or all 4s. We can only choose one because picking one deletes the other one. Right, okay. So you're saying that we start from the smaller values and we compared the first two and uh, use the local greedy algorithm to compare which one gives us better rewards. That is compare 6 and 8, and 8 is of course giving us better reward, so we take 4. Yeah, so the greedy answer would lead to picking 4. Unfortunately, this prevents us from picking 5. Right. That because only a local optimum. Perhaps a different greedy strategy would work. How about sorting the keys by how many points they give? And then greedily try to pick the most points. We would take the 15 because we got 3 occurrences. Yeah, the greedy strategy, it won't work like this either because you really need a global strategy. Taking one locally, large rewarding value, it may not be really optimal. It could be tempting, but it's not optimal. Okay, now we're talking about DP. We'll skip the underlying details of DP, that's fine, because we have been covering that in our previous episodes, so it's good for me to skip this right now as well. Article stays focused on the problem. Formulate DP in 3 easy steps. First, we need some sort of memory that stores the answer to our question or sub-problems. Because we're doing top-down, we use a hash table for memory and a recursive function. Right. Let's declare a function max points. We want max points num to return the maximum points that we can gain if we only consider all the elements in num with values between 0 and num. Okay, so you're defining your subproblem as a max point problem uh, of elements with values between 0 and num. Okay, so it has an inherent order in it. The second thing is we need a recurrence relation, a way to move between states. Yeah, you can call it like a uh, state transition function, or you can call it like, yeah, let's just call it a state transition function. Let's say that we're currently at some arbitrary number x, at some arbitrary number x, where x is the nums, well, x is in nums one or more times. How can we find max points x? Okay, so yeah, again, what this means is like we only consider elements in nums with values between 0 and x. Interesting. So it's sorted and uh, it's a subset of all the numbers in nums. Right. When it comes to x, we have to make a choice, take or don't take. Okay, that is exactly the heuristic we were having earlier, but we somehow abandoned it. But anyway, let's see how you do it. Um, if we take it, then we gain points equal to x times the number of times x occurs. Right. We can pre-compute those values. Right. For now, let's call this value gain. Okay. However, because of the deletion, by taking x, we're no longer able to allowed to take x minus 1. And we don't have to worry about x minus 2. Wait, sorry, we don't have to worry about x plus 1 because x plus 1 is automatically excluded in this set. Yeah, because the maximum would be x, so there's no x plus 1 in this set. So the largest number that we can still consider is x minus 2. Okay, I think this kind of like this way of separating subproblems or uh, mm, yeah, defining subproblems is really helping you out because then you don't have to deal with this case that I was dealing with, which will um, I mean you didn't have to deal with this take 4 because you see I had to really consider this case. Uh, if we don't take 3 or if we delete 3, but if you define the subproblem as only taking nums, elements in nums that is between like 1 and some x maximum and some x, and if you're only acting on, you know, the edge value, the largest value, or the smallest value, then you only need to deal with two cases, just like this, right? Just like when we take actually the smallest value, yeah, if we actually exploit um, the ordering of things, and we start, just from the corner, either the smallest value or like the largest value, then we can actually have an equation like this uh, of either taking that corner value or not taking that corner value. And because we're doing things in an order, now if we're not taking the corner value, then that means we are definitely taking the value next to the corner value, right? Uh, yeah, it's kind of right because I think the separation of either take or delete, I still believe that the take or delete is the right way to categorize it. And in this case, because we're starting at a corner, the only way to delete a corner value is to take the value next to it. Right, right. So I think at this point, I don't need to read further because I already have an idea of what to do. Um, yeah, and uh, and yeah, I think I already have what I need. Let's just be bold and naive, and let's go back to this and fix our problems, and we can have uh, a working recursive relationship. Okay. So right, we're still going to use a dictionary. That is still correct. Uh, and instead of focusing on number one, we are focusing on, yeah, let's say the largest number. Yeah, let's say we're gonna focus on the largest number, and we're gonna basically let's delete everything below here because yeah, when the that equation was too long. So we are going to focus on, in this case, focus on the largest, right? Focus on 5, the largest. Focus on the largest. And now we have to, change this expression here. And our R, yeah, now we can define what our R stands for. Now, R of 5, what this means is that it means the reward of um, the reward of mm, uh, all values, all elements in nums that satisfy one less equal to k less equal to 5, right? All elements k, yeah, in nums that satisfies elements k in nums that satisfy uh yeah, this is like, I apologize for my handwriting because my sketchboard is really small right here. It's like a half-foot long sketchboard. um, I may upgrade to a larger sketchboard later. um, Now, yeah, so this is what R of 5 means. And because, it's like all the values, right? All the values with maximum of 5. Um, so we follow this bisection logic of either take it or delete it, right? So 5, it first has to exist. It has to exist in the nums list. If it does not exist, we go directly to the next one, right? Like that is if 5 actually exists in nums list, right? And if not, then we're gonna say R5 equals to R4. Right, because if it's in there, we're gonna do it. If it's not in there, we're just gonna dial down, or we're just gonna uh yeah, reduce 5 to 4 and try again. Uh yeah. So this condition has to be added before the max. Otherwise, we're just gonna use this R5 equal to R4. So now, if 5 indeed exists in nums list, the first option is to take it, and then what we're left with, this is gonna be good. Now, what we're left with is basically R3, right? Because if you take 5, that means 4 is gone. So you're gonna have to work with R3. And then the other possibility is that if you delete 5. So if 5 exists and the only way you can delete 5 uh, is to is to take number 4. But again, this is on an if, right? This is on an if. If, the number 4, it exists, it belongs to nums. That is a condition you have to follow. If 4 does not exist, then basically this part is like nothing. Yeah, so what about this remaining? thing here. So we're basically talking about, because we took 4, now we have to work with R2. That is if 4 exists. Right, right. So otherwise, right, otherwise, otherwise, you know, otherwise this part is 0. Because, because if 4 doesn't exist, there's no way you can delete 5. So you're only gonna work with the case where you take 5. Right. So I think this is it. So we have our expression. We just haven't, generalized it into a uh, in terms of like k. So let's do that. So now in general, our expression of r k, right? Where k, it could be an integer smaller than, k is an integer smaller or equal to, the maximum value in nums. Um, but also it's greater or equal to 1. Uh, because, the smallest value element can exist in nums is 1. So rk um, is based on an if condition. Uh, so the easier case is what is rk minus 1 if uh, the value k, it does not belong to nums, right? And then in the case where it does belong to nums, it'll be the maximum between two values. Uh, the first value is r of k, that is the value of taking uh, all the k integer, and then plus the remaining subproblem of r k minus 2, because by taking k, you have eliminated k minus 1, and the next largest possible integer is k minus 2. Yeah, so this is like take k. And then if we want to delete k, there's again an if condition. If k minus 1 actually exists, right? If k minus 1 exists, if k minus 1 exists in nums, we're gonna take r of k minus 1, that effectively deletes k, and then we are left with the remaining problem of r k minus 3, right? Uh, and then if this value does not exist in nums, then there's no way we can delete k. Not in this context. So it'll be 0. So we're still taking the maximum between this and this. Actually, you know what? This last option, it could be deleted because we're taking the maximum. The maximum of something and 0 is something you don't really need to consider. But just for the logic completeness, we're going to write it here. And this is like delete k. Yeah, take or delete. Uh, yeah, exactly. So this is our expression, and now we are just going to implement it, right? Yep. Now let's take the description of the problem, and then we are going to open up a new Leetcode uh, notebook. Let's close some of these and create a new notebook. We're going to name it Leet, and today's problem is 740, right? And mark down 740, delete and learn. We're going to copy the description here, put it here, and let's try to make the middle part um, kind of like a, well, um, how do you make it a item? Right, you do it like this. Right, and then we're given an example. I'm gonna put that example here as well. Right, and here comes our solution, tentatively. Um, so this solution here, it'll consist of two processes sequentially. The first one is that we're gonna have to, convert nums into uh, a dictionary, right? So I'm gonna say D equals to uh, 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 yeah, list to dict of nums, right? And then let's just write return 0 for now, and we're gonna define our list to dict um, function as so we have the we're gonna pop, right? Like we're gonna pop. So yeah, we should probably define the return type. Input type and the return type. It's going to be a dictionary. And this is like converting a list of integers into a dictionary with the dictionary. The keys are the strings of the integer. You know what? Actually, I think maybe we should use hash map instead of dictionary, because dictionary only support Python identifiers as keys, but maybe hash map can use integers as keys. So let's see, hash map. Let's see, how do we do hash map in Python? Okay. Mm, So how do you define it? I don't see like a very clear definition here. Maybe just let's skip that and say hash map. Python dictionary is a built-in type that supports key value pairs. Right. Hash map in Python. That's what we're looking for. Is there a hash map in Python? Oh, built-in dictionary data type. All right. So while the solution was like saying something about hash maps, maybe it doesn't really have a hash map in Python. Do you? Um, I don't see a hash map here. But, in Java they define a hash map, data structure, but in Python, what is default dict? What is default dict? I don't know what that is. Let's just look it up. Python default dict. Uh, di okay. Default dict. Default dict is a container like dictionaries present in the module collections. Default dict is a subclass in a dictionary class that returns a dictionary-like object. Default dict never raises a key error. It provides the default value for the key that does not exist. Okay, it will have a default value for any key. Interesting. But it's still a dictionary, right? And you are somehow pre-computing in this way, and hey, you're using integers as you're using integers as dictionary keys. I thought that was impossible, but you just told me that it's possible. So maybe I was wrong. Maybe actually we can use that. Okay, let's try it. The keys are the integer. The values are are the total reward and that of that integer, of taking that integer. Okay, so let's see if it's possible. All right. Um, so the way we turn it into a dictionary is that we can use a for loop, and we're gonna taking each of the numbers in the nums list, uh, and we're gonna create a, a key value pair in the dictionary, right? So let's just create an empty one, right? D equals to an empty dictionary, and we're going to say D of num equals to uh, that, well, I mean, we're going to have, right, okay, so yeah, so it is the value itself, right, equals to num, right, and that is if it does not exist before. But for repeated values, we just need to add to it, right? Yeah, how do we add to it? Mm, basically, we're gonna check if, um, you know, if it is a key in there, right? Python check if um, dictionary has key. Uh, right, has key. Got it. So if d dot has key of num, and then if that is true, we're going to just add the number to it. Else, d of num. If not, we're gonna recreate the key. And that's it. I mean, this is it, right? So, yeah, let's just test it, okay? We're gonna make a test case. Test cases. S equals to solution, and then we're going to see right, print input, let's say, because the order doesn't really matter, I can just do it like this. Um, and what do we expect? Let's just test this list to dict thing. Expect the dictionary to be 1 1 3 1 4 1 5 2. Actually 1 2. We have two ones. Right. So print s dot list to dict, and we are going to see if this happens. Right. Dict object has no attribute has key. Really? I thought has key works. Oh, removed from Python 3. Okay. If key to find in example. All right. So if this method is gone, if num in D, whoa, wow, wow, that is pretty cruel. So maybe this is like not the right way to do it. Check if keys is using get, using keys, in keys. Yeah, I think this makes more sense. Um, in that keys, right? That would make more sense. It still produces none. I wonder why, but let's uh, let's find out why it is not doing the job. I'm gonna put like a breakpoint here, and then nums is a list of values, right? And then if we just step, first one is probably else, and then probably gonna add something to D. Now it has 1, 1, which is good, okay. Oh, I see. Because we're not returning anything. That's why. That's probably why. We need to return D. That's why. Right. Whoa. Yeah, I think we're right. So for 1 we want to return 2, for 3 we want to return 3, for 4 we want to return 4, for 5 we want to return 10. So yeah, it is now correct. Great. And this actually I guess solved one of my previous misunderstandings. Previously, I thought like dictionaries couldn't use integers as keys, but I was wrong. I'll definitely go back to that video where I said that and make a correction down there. Um, like yes, you can actually use integers as keys in dictionaries. I was wrong. Yep. And now we have validated this function to be working. Now we go back to our main delete and learn problem. So because remember, this is only the first step, right? Step one, convert the list into a map or dictionary of total rewards. And the next step, step two, what we're doing is that we're going to now use the recursive relationship that we learned from the solution and derived a little bit on our own uh, and implement it. Does this look like a top-down approach or a bottom-up approach to you? Um, I think we can implement a top-down, right? If we do a top-down, that means we're gonna do recursive calculations, and we may call we may have to reach computations that yeah, we're gonna do a top-down computation. Let's just do that. So we're gonna have to also make a function that says uh, r, right? Function r. Um, function r of what? A function r of a number n in there. So this is like uh, the maximum r of n is the maximum reward uh, of using the elements between 1 and n in the original nums list, right? So I think as an input, you also need to pass down the nums list. Right? Unfortunately, I think so. So type n is an integer. Type of nums is a list of integers. And return type, I think it is an integer because all the rewards are integers. So you're also going to develop something that stores the value, right? Yeah, let's just call it reward, right? And we're going to look up if it's already like remembered. So here we go. Um, we're going to build I guess we're going to build uh, a list. Um, at least to store rn the maximum reward of using the element between 1 and n in the original nums list. Right. So the first thing we do is we look up that if it's already in there, then we just read it off. If n is let's say if n is smaller than the length of r, right? And we're just gonna look it up, return r of n minus 1. Yeah. Else, if it's not readily available, uh, if it's not readily available, we're going to basically do what? We're basically going to maximum reward of using the elements between 1 and n in the original nums list. Um, is this where we use the is this where we, let's say, use this recursive relationship? I mean, we have to use it somewhere. Is this where we use the recursive relationship? Well, let's go back to the main function here. And step 2, after we convert the list into a dictionary of total rewards, um, we're going to um, use a top-down approach, right, in DP to uh, to calculate, uh, for example, R of uh, right. So let's just find out, D keys, the maximum number in it. So we're gonna call it mmax, right? R of mmax. And to calculate R of mmax, we're gonna use the recursive relationship. Right, we basically return reward mmax and nums. We just pass nums down instead of returning 0. So definitely because of this, we're going to write down the recursive relationship here. So if we don't yet have, if we don't yet have the length of that, we're just gonna be calling ourselves, and it'll be like this, right? There's like an if, right? There's like a big if condition here above all of this. This is right. We're gonna write this as if k is indeed inside nums. Right. So we're gonna start building up cases here. If uh, if the number n, actually, now that you said that, we should probably put k here. Shall we use k or shall we use n? I mean, we are using k here, so let's be consistent and use k here as well. Reward k between 1 and k in the original nums list. Right. If k is less than the length of that, well, is this correct? Because eventually, eventually, this list, um, the first one will be corresponding to the value 1, right? So yeah, so um, the first element in list R will represent the value of reward 1. Yeah, so it'll be like what? Reward 1, reward 2, etc. So for the K here, if you want to look up reward 2, then we need to make sure that the length of R is at least 2. Right, uh, so it should be less equal to. In this case, if we're looking up just K of 2, and then the length of R is actually 2, then we actually make it. Yes. Yeah. Else if else if uh, K is in the nums list, right? Um, Actually, I think if we look it up in the list, it'll be pretty expensive. If we look it up in the dictionary, it'll be cheaper. So how about let's store D. How about let's store D as a property, right? Right, right. Okay. And then now we can now use self.d.keys, and if k in that, if k is in that, then we can calculate rk as the maximum between these two. But depending on whether k minus 1 exists in there, we are still going to have two different cases, right? So yeah, k minus 1, if k minus 1 in self.d keys, uh, if it's in there, we'll take the maximum between this and this, rk plus rk minus 2. What is rk? So rk is basically if you look up, right, it's basically looking up self.d, look up the key k, right? We're gonna put a max in here, self, that is rk basically, and then we're gonna do uh, uh, r of what? Self.r, uh, k minus 2. Here we go, r k minus 2. And the other one is um, r of k minus 1 plus capital R k minus 3. Right. So self dot d k minus 1 plus self dot r uh, k minus 3. It's just one case. Else, if k minus 1 is not in the dictionary, we're trying to maximize 0 and this, so it's just this, the first value. We don't need to perform max anymore. Right. And if, you know, if k is not in the dictionary keys, we're just gonna pass capital R k minus 1. Uh, R k minus 1. But because we're doing things like in a top-down version, and at the beginning, we don't really have, excuse me, all these values of k minus 1, k minus 2, and k minus 3. We're gonna have to call the reward function to build them up. Right. Unless we want to do it the bottom-up approach and calculate those smaller values first. Otherwise, we're going to have to, let's say we're going to have to, uh, instead of saying self.rk minus 2 because you didn't have it yet, you're going to have to say reward, self-reward k minus 2, and of course nums. Are we using nums at all? Actually, since we're not using nums, we can remove it, right? Yeah, that's a good idea. Like we're not really using nums because we're using self.d keys to see if k is inside the original um, list of integers. So that's good. So self-reward. This is also self-reward. So now we're using the recursive function to call itself. This is going to be a top-down approach, of course. And we're going to do that. Else, we're going to do self-reward k minus 1. But, since you're using, values of k like k minus 1, k minus 2, k minus 3, you better make sure that k is at least greater or equal to 3. Otherwise, this index will be below 0. So you really want to maybe, initialize 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 our R0, R1, right? R3, R2, and then maybe, yeah, then you can do that. Also, there are cases when um, the length of nums is, equal to just 1. Uh, well, then you just return nums 0. Else if length it's equal to just 2, that's well, in this case, you're still gonna find out if they're adjacent to each other. And right, maybe this is like else, and you return that. Mm, but once you get into return D, uh, nums 0. If we have more than 2 values, we're gonna need some kind of recursive relationship. And let's see, reward and max nums. Right, we don't need to use nums here, just use a max. The reward function here, well, don't forget that self prefix, and don't forget don't forget this. Right, we need this everywhere. And if we're calling like the reward function to do the recursive relationship, we want to make sure that um, the k has to be greater or equal to 3, right? How can we guarantee that? Well, first, if our stored calculation of R has this value here, has this value, um, for example, if k is 2, right? And we want to see if the R list has 2 elements. So we're going to compare k with length of R. If it actually has 2 elements, then then R will become 2, and 2 is less or equal to 2, and that is true. And we're just going to return, right, the kth element inside the R list. Uh, right. So if this is not true, it doesn't guarantee that k is going to be greater or equal to 3. Right. Right. So what if k is like 1? It looks like we need to at least initialize some of these. So what is R0? Well, according to our heuristic, R0 here, it means uh, well, what is R, the first element in the list R? Well, the first element, it means, yeah, we're only looking at integers between 1 and 1. So that is, all the values of 1 if it is there. So yeah, so self dot r 0, it is you know it's just simply this. If we only have integer ones, and what is r of 1? Well, that is if we only have values of ones and twos. And if we only have like values of ones and twos, what do we do? If we only have like ones and twos, we can either take 1 or take 2, right? So it's going to be the maximum between self d1 and self d2. Take all ones or take all twos. And this is take all ones. And what about self.r3, r2? Well, if you have like 1, 2, and 3, there are two choices. You can either take all the ones and threes, or you can take all the twos, right? So I'm just gonna, yeah, self dot d1 plus self dot d2. It's all of that. Uh, or self dot d, uh, that's 3, and this is 2. Either take all ones and threes, or take all twos. Right, so we initialize them, and hopefully now we can go directly to this reward function. And now, because the first 3 elements have been calculated, right? And this requires that, k is at least 3. Uh, right. And when we use k equal to 3, we're gonna look up R2, which is already there. So yeah, so if um, that, right, if that or um, k is less equal to 3, yeah, then we can do that. Else we're gonna do this. So I think that's kind of like complete now. Uh, and we don't need this else condition, right? Once we initialize that, we can just return this uh, because once we send the nmax in there, we're going to start the recursive computation uh, procedure of first getting into uh, these things and then getting into those things. Right, right. Uh, but yeah, but what about this? What are we expecting for these things? So for this dictionary, 1, 3, 4, and 5, um, 3, 4, 5, we either take 3 and 5 or we take 4. In this case, we definitely take 3 and 5, and that'll be 13, and plus this, that'll be 15, yeah. So for the real test cases, um, for the real test cases for this delete and learn function, expect 15 here. First one, we expect 15, but let's just add a few more test cases here. 3, 4, 2, expecting 6. Input this, expect 6. Um, we can have one more test case of this, and we're expecting 9. One more test case, expecting 9. Right. So let's just run that. Run this. Run this. Something's wrong. Okay. We're missing something called self. Right. And let's just do it again. Right. List assignment index out of range. Really? Uh, Step 2. Okay, let's use a debugger to find out why that is out of range. Okay. Now we're here. Self.r is an empty list. Oh, okay. Because that's not how you append a list. The syntax for appending list was wrong. So, okay, let's see. Append, right? Am I doing it right? Like Python list append to the end. Right. So if we append and then we insert the value, yes, that's how you append a list. Right, that's how you do it. And then let's append again. And let's append again. Right. Hopefully now it works. What does that mean? Key error 2. Okay, so for self.d, you're telling me you didn't have a value of 2, right? Because in the first one we don't really have any 2's. That's true. So, right, so it has to be on a condition. D2, I mean, it's like if D2 exists. And that is if 1 exists, right? Right, so yeah, these appending and initializing, they're conditional. You only do that when this exists. So if uh, 1 in self.d.keys, we're going to append this, else uh, we're just going to say we're going to append 0. Right. And for the next value, yep, this kind of sucks, you know. There's so many if conditions that you need to add. D1, D2, it's like if they exist, then you append them. If they don't exist, you're just gonna have to replace them with 0. Uh, so let's see. Take all ones or take all twos. Take all ones and threes or take all twos. Right. If we want to take all ones or take all twos, if they exist. Right. If they exist. Same thing here. If they exist. So this existence thing is really creating a trouble for us to initialize. Can we make this syntax a little bit more elegant? I guess we could make a staircase of ifs. If 1 is in self.d.keys, We're gonna do sum1 is this, else sum1 is 0, right? Does that work? I mean, 1 in 1, 2, that's true, right? Okay, does work. Okay, so if 2 in self.d.keys sum2 equals to self.d2, actually, you know what? I think I can make a function out of it. Def uh, um, immediate take the, yeah, sum x self and x, right? So this is gonna be interesting. Now type x integer, and then return type is integer. And what is it? Like return the yeah return the reward of taking an integer x from this from the uh, from the original nums list. If x does not exist in nums, return 0. So we can just do that. If x in self.d.keys, we're going to return self.d x else return 0. Right, so I don't have to do that anymore. I now have built a function for it. Now, right. Now we just say append self.sum x of 1. Yeah, right. So there we go. Now this is sum x of 1 or sum x of 2, right? Yeah. And this is sum x of 1 plus sum x of 3 or sum x of 2. Right, if they exist. Right, so I think, well, we definitely need that self prefix for all of these sum functions here and there. Okay, so hopefully now we have a working, no, not really. Where is that? return reward, return R. Okay. So for all the R's in here, because it's like a class property, we're gonna have to say self.r everywhere. Yeah. Okay. Oh, okay. There's some syntax error. Syntax error. Um, Not supported between instances of list and int. Really? I mean, k, it is supposed to be a integer. Reward k, right? Yeah, k is supposed to be a. Ah, okay. Because I've been using the square bracket inside that, and that was wrong. So now this should be okay. Well, that turned out unexpected. So now the program runs, but the results are bad. For this one, we're expecting 6 because, let's see why we're expecting 6. Delete 4 to earn 4 points. And therefore, 3 is also deleted. Uh, and then we can have 2 points. Right. And this we're getting too much. Can we just focus on the simpler case and then find out what went wrong? Yeah. So 3, 4, and 2. Let's see what happens in here. We're going to use a debug, and we're going to put our breakpoint there. Right, so nums is definitely a list like that, and our maximum number is 4, so that did its job correctly. And now we're trying to append and self.d, I think self.d self.d, it should be a dictionary that records their respective total rewards of taking each of them, which makes sense. And R is now like an empty one. We are now just initializing R0, R1, and R2. So what would be R0? R0 would be like the maximum reward of taking values between 1 and 1 inside the nums list, because we don't really have a number 1 here, so it'll just be 0. Self.r. Right now it's just 0. The next one is R of 2. And because we do have a 2 in this list, it's going to produce the value of 2. Right, and that's correct. And the third one, and we're exercising this logic here. So that is like calculate the value of taking only values 2 and 3, and apparently that is going to be 3, right? Because you're going to take 3. Yes, and that is correct. Now we need to return the reward of mx. Mx is what, number 4. We really want to step in now. Yeah, now we're in here. and inside reward function. And because our k now is 4, we're gonna see if k is less than the length of self.r. So our self.r is a list of length 3. So apparently we cannot read the answer directly out of the first 3. So we're definitely gonna have to go to the else condition. Uh, and we're gonna see if k is actually in the list of d keys, self.d keys. Keys, yeah, it is in the keys, right? So it's going to jump into that if condition. And then we're going to ask ourselves if k minus 1 is in the d keys, which is like 4 minus 1 is 3. So 3 is indeed inside that. Then we are going to return this expression, right? So we're going to return self maximum between those. So dk again, dk is dk is going to be d4 self d4. It's like, so the first one in the max bracket is the option of taking this number k. So taking number 4. So we take number 4 and it's going to produce 4. And next is and then because we took 4, we're going to now have to calculate the reward function of 2. And the reward function of 2 is like use the numbers up to 2. And that is going to be 2. So the first one is going to give us 4 plus 2, which will, which will give us which will give us 2. Locos, globos, right, which will give us 2. So this one is supposed to be, um, 4 plus 2 is 6. And self.d, k minus 1, and that is 3, right? So the value of that is also 3. It's plus self.reward k minus 3. So k minus 3 in this case is going to be reward 1. And reward 1 is r of 0, which is 0. So basically this is 0 and this is going to be 3. So 3 plus 0, that is going to be 3. Uh, so overall it should give us 6. But let's step in and see what is k right now. K of 2. Yeah, let's see if k of 2 actually returns us 2. Uh, we're expecting a 2 here. Right. So because k is less than 3, so we already calculated it, right? So we can just return r of what? Return r of 1, which is 2, right? Which is 2. Yeah, I mean, that is going to be right. And then now we're doing like k1. K1 is probably 0, right? Uh, Now we're out of it, and I think think it should return us the value of 6. Right, it is 6. Okay. Strange. So this turned out to be correct. Let's try this one here. Oh, whoops. We just opened a new tab. Um, let's turn this off. So it was correct for that one solution. So I don't know. Maybe it's because, you have to build one. Um, yeah, probably it's that you have to build one for each of them. Right, that is the problem. I think maybe our algorithm is correct. You just have to, reinitialize. Right, you have to reinitialize um, everything after you return it. So for each problem, you have to rebuild it. You basically have to return that, but then you want to clear. Yeah, how do we clear? How do we clear these things after? I mean, if you want this to work, you're gonna have to call, recreate an instance at each time. Because I think by doing that, wait, wait, what are we doing here? That is weird enough, right? How come? How come? Like when we were doing it, 15 and then 2 and then 9 and then 2. I mean, why? How do we clear? Yeah. How do we clear the values? How to clear a class object Python, right? Create, delete, initialize class property. Using the del keyword. Delete. Delete object properties. Okay. So, well, I mean, when we were when we were dealing with just one of that, it was correct, right? And when we're just dealing with that, well, it is no longer correct. But if we refresh the definition, it'll be correct again. So, I mean, this is a very weird behavior. To be honest, this is a very weird behavior. We seem to we seem to have the solution, but you know what? But then if we run the second time, it probably will fail, right? Yeah. Expected 6 and 9. Yeah, that is quite weird. That is quite weird. Like, I don't know why. Individually they work after initializing the solution. But then once we run it again, it fails. So what is this problem? I am a little bit upset, but this is probably a general Python syntax problem. Like I have to reinitialize the definition of the class in order to make it work. So it's some of the storage in it. So yeah, let's just you know, initialize that, okay? And we're gonna find out. We're gonna find out using the debugger. Now, you see, this works. Second time it didn't work. Yeah. So we're going to use the debugger and we're gonna just run it once. Look at S, right? It's got 342 and a length of 3, and that looks all correct. R, it's got 0, 2, 3, and that is all correct. But if we just run it again, let's see what does our dictionary become. Right, you see, the dictionary itself has doubled the value there. And wow, our R list actually grew as well. So I think we have to somehow delete the solution each time we run it, right? Delete the solution object. Um, delete S, for example, delete S, and then recreate it. Maybe that'll work. Whoops. Excuse me. Nope. 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 How about let's just say S1, S2, S3. Yeah. And then we use S1 here, S2 here, and S3 here. Still, it does that thing. It's almost like we need a deep copy. We need a shallow copy of the solution object. It's almost like we're causing this to fail. It's almost like we're causing this to fail by recreating stuff. And you see, wow, look at that. You see, it's like multiplying on itself. Each time you call the solution, each time you create a solution object, you are um, you're taking some of the previous memory and then multiplying the dictionary and multiplying the and extending your art list in a way. You're like appending and appending. And that is something I don't want happening. Um, self list to dict. Well, let's see if we can find some similar expression in solutions to help us debug this thing. In this DP solution, we're pre-computing, right? I did that too. We're pre-computing like this, list to dict. For the solution, it's using just a for loop. And what is this add cache? Add cache. What does that do? Python add cache. What does this add cache do? Function caching. How to cache with Python, advanced Python, decorator Python, Python cache modules. So cache LRU cache decorator, which gives you the ability to cache the result of your functions using the least recent used strategy. Right, so I think that's something maybe Python is doing. Add func tools cached property. Okay, so you are doing that. Um, add cached. So, hmm, this add cache, you're probably using the cache. But for me, actually, for each of the problem, I don't want any cache. I don't want any cached memories, right? Uh, Python 3. Okay, you're not using cache. Default dict. Recurrence relation. Return that. Um, so my question is, how can we save our code? Because our code is okay except that it has the cache. Like why does yeah when I create a different when I create a different object, it seems to right it seems to take the same cached attributes. I mean, look at that. I mean, definitely that cached something. Right. So why does Python cache class? Oh, destroy. Yeah. So how to destroy a class instance? Python del the object. I mean, I tried that earlier, right? So I said dels1, dels2, and dels3 as well. Still, it still gives us the wrong answer. For oh, okay. Let's actually delete s as well, so that we don't have anything here anymore. Well, we have nothing but class function. Now we have nothing because we deleted them, but still they give us the wrong answer. I just don't know why. I just don't know why that having this is going to affect me running the next code. Like if I comment out everything else and rerun the definition, it's going to work at least for the first time. And I want it for the second, and I run it for the second time, it stopped working. It stopped working. And we'll have like very long and very weird locations. So it seems like it's sitting on the same memory. Yeah, it seems like every time I create a solution object, it sits on the same memory. Uh, and these things and these attributes, they also sit on the same memory. So what I need to do when I call every one of them is to, yeah, how do we clear self dot d delete self dot r, and then we're gonna just initialize self dot r equals like an empty string, empty list. Something's wrong. What is wrong? attribute error, delete self D. Okay, so maybe we don't delete it there. Maybe we just, comment that out and we just initialize it in here, right? What's wrong? Solution object has no attribute D. Right. Yeah, because we haven't initialized it yet. List dict. So we initialize it here. Okay. Um, how about we just define an initialization here, right? List object has no attribute keys. Okay, so D is dictionary. Okay, huh? No, it actually worked. So, okay, fine. I think now I see what's wrong, and that is a really really good lesson, guys, because this is something that I spent such a long time to just finally find out. And I bet that if we just say S, now it works too. Yeah. Okay. So guys, I basically spent the last 20 minutes to find out why when I call each test cases, it's gonna give me a correct answer in the first round and then wrong answer all the way afterwards. And the reason was because I was defining something, you know, in between the class definition scope and my function definition scope. I was thinking that, by writing things there, we're going to just initialize R&Ds. But it turned out they are some kind of like global variables, global variables that you cannot delete even after you delete the class object. That was just such a hard lesson, global variables here. That is the only explanation. Right, right. That's the only definite explanation. So global variables don't even vanish after you destroy the class instance. Yeah, so the best practice is to not use them unless you know what to do, unless you know what you're doing. Right, right. This is such a great lesson, and I can't stress enough how much doubt, self-doubt I've been going through trying to figure out what's wrong. It was both my arrogance and ignorance that got me there. Anyways, now we have a piece of code that is supposedly running correctly, and let's just submit it to see if it's working. Whoops. There's something wrong. It says unsupported operand types for plus, int, and none type. Okay, we have a test case that actually made us look bad. So we will look into that and we will see what's the problem. Now, we're going to put this test case in there. We don't know what it's expecting, but oh wait, are you doing that again? Like, let's actually, clear the kernel, clear all outputs, and restart the kernel. Uh, I think maybe, oh, okay. Maybe instead of putting D here, we better place it um, not in the init function, okay? Um, right, so each time when we call this function, we want, first of all, um, self D to, just to, clear the content for each problem before, yeah, for each problem. Clear the self.d content before each problem. So I think that will at least make it right, yeah. And for this one here, we can see it's creating some problems, but that's fine. We will find out exactly where it's creating a problem. Unsupported operand type for plus between integer and none type. So you're telling me the first one here is an integer and the second one here is a none type. Well, that is kind of weird because I did not expect that to happen. Um, so we turn that on and we're gonna put a thing there. We run it and we run this. So let's see. Oops. Right. So yeah, I need to know where exactly did it get into there. So the first time there, okay, we had a breakpoint. We had two breakpoints. Right. Is it going to work? It is not going to work. Okay. So let's just, whoops. I think we need to restart the kernel. And we set a breakpoint on line 72. We run this. So self.d k is 8, right? Like self.d k. Well, yeah, self.dk it is It does exist, and it is 8, right? So this one exists. And what about self.reward k minus 2? You're saying that is a none value. So k minus 2 is 6. So we're trying to do reward 6, right? Yeah. So now 6, when 6 is less or equal to self.r, what is the length of self.r? Uh, okay, so now we're at the beginning of building this R list. So right now we only have 3 initial values, and that's okay. So we're gonna go to else, and let's see if k is in D keys. D keys 6. Number 6, 6 is not in D keys because we don't have a value 6. We don't have a value 6 here. So it'll go to the else condition. And we're basically going to say, hey, the number 6 doesn't really exist in the keys. So if you want to take all the take all the rewards from the from 1 up to 6, it's going to be the same of 1 up to 5. So we're going to step in, and then we're going to talk about 5. And now 5 is still um, greater than that length. So we'll jump into else condition. And 5, I think now it is in the dictionary. So we're going to get into here. And we're looking at if 4 is in that dictionary. And the answer is yes. So we're going to return this. The maximum between self d5, which is d5, which is 5, plus self reward k minus 2, which is self reward 3, right? We're going to have to step into it later. And then the next one is self.dk minus 1, which is in this case self d4, which also has a value of 8. And then when we need to look up reward k minus 3, we will be looking at 5 minus 3, so it's reward of 2. Anyways, we'll step into it and let's see if there's anything wrong with k equal to 2. When k equal to 2, we're going to basically say, hey, now it's less or equal to 2, so we're going to just use R2 there. And what is our R2? Well, it's 4, right? And so we go ahead, and now um, we're looking at reward of 2. So because 2 is there, I mean, it's 2 is less than or equal to 3, we're going in here, and R1, we also have a value of it, which is 1, which is fine, which is okay. And so now we're back here, right? And K10, we are back here. So at this point, let's see if we already have those things there. So D of 10, we got 20. Self-reward, self-reward of k minus 2. Uh, k minus 2, k is 10, k minus 2 is 8, um, and a reward list. Oh, I mean, I think we have found a problem here. Um, because what, you're not storing it. You're not storing, um, you're not really storing. I mean, you are doing a job of back like top down recursion just fine, but you're not storing the value. Right, you're not storing the value. You really want to store them here. So self R, right? Because you want to append and you want to look it up. And how do you look it up? Well, shall we actually, shall we actually, instead of appending them like this, we make them initialize all with all zeros and then add, just assign the first, second, third element as those, so that we wouldn't have a problem of updating it here. Because now, since the list is very short, each time you have to append it. And this reward function, when it cascades down, it does not allow you to append the list like that. Instead, you can only assign the list in a certain way. Yeah, that's true. And how do we, um, can we like just initialize? Yeah, can we initialize list Python with nuns? Can we do that? Set to none. Initialize n size none value to a Python list. Oh, okay. Okay, that's what I'm gonna do then. I'm going to initialize it as none times n and max, because we know and max is what we need to do. And then, yeah, so now this simply becomes r of 0, and it is equal to this. And now this becomes r of 1, and it is equal to this. And this now becomes r of 2, and it is like this. Yep. Right, so like initialize with none, with nuns. So now this if condition needs to change. We're going to basically say if self dot r of k minus 1. Yeah, check if like a value is none, right? Python check if value is none. Check if a variable is none in there. Oh, okay. Is. Use the is keyword. All right. If is not right. Right. So I think it'll work, right? So is none. This will be, well, is didn't work. Is keyword to check. How? A equals to none. If A is none. Oh, is none. Okay. I got it. If that is not none. Let's try 1 is none. Is that true? Wow. I don't know. What's going on? None equals to none. It's true. Okay. 1 equals to none. False. 1 is none. All right. Didn't work, but double equal sign worked. So I'm going to just use that. Uh, so is none, or actually is not none. Yeah. So Python not equal operator. Right. Okay. So I'm going to use that. So if this is not none, or that is less or equal to 3, we're going to run this. Uh, and each time when we found a solution, we're going to append it, right? So self rk, actually k minus 1, because yeah, the lists use 0 indexing where our integers start at 1. So we're gonna have to do a minus 1 here when we come to the list indexes. Um, Now this is going to be how much? Self rk minus 1. This is going to be this thing here, right? And we're going to return this. Um, Same here. Else we're going to store it in here. And we're going to return this thing here. Right. Just store into R and return. Same here. Store into R and return. Yeah. Now I'm going to restart the kernel, clear our outputs, and try it again. Because I think now I have a correct implementation by initializing it with a non-matrix, a non a list, a list of nuns. All right, we have some other problems. Okay, 75 for integer and none type. Again, we have a none type, huh? How about, let's say, we start with a simpler problem like this. Does it work? It does work. It does work multiple times. Uh, so this problem seems to happen only when we have like a large test case, right? And it happens at line 75. Self R, self reward. So this self D, it definitely worked, but when we were working into self dot reward k minus 2, um, then it stops working. So at some point, I think the chain of value assignment was broken, but it's okay. We can still find out where it happened. Now, our k is at what? At 8. Why is our k at 8? Because, I mean, shouldn't we go with 10 here? Reward of 8. Is this going to cause me problem? Yeah, it is. All right, so let's just say, hey, what's going on? Stop that. Let's just say we need to restart the kernel. And we will put a breakpoint there. And then self d of k, self d of 8, it does have a value of 8, right? Yeah. I mean, mx, shouldn't mx be like 10 or something? I think so. So why would it actually why would it go into there? Yeah, that's what got me really confused. Why would we look at reward 8 first? Shouldn't we be looking at reward 10 first? Well, what is it? Oh, we didn't start the debugger. My bad. Now we are looking at this, okay? And then we're gonna run it. We're gonna run this. And max is 10, right? So if we step in, uh, oh, okay, because for nmax we really didn't trigger this else condition. It's only when we go into the case of 8 that we actually triggered that. So yeah, now we're in case of 8, and on self R7, take a look at our R list, right? It has a length of 10, makes sense. But R7, right now we don't have it. We're gonna have to build it, right? So let's step into it. Now we're building what? We're building k equal to 6. Uh, and because right now in our R list uh, we don't have R5 yet, so we're gonna jump into the else condition, and it turned out that we really don't have 6 in the dictionary anyway. We're jumping directly into reward k minus 5. Right, so let's jump into it. So reward 5, now we're looking at our mm, our list. It still doesn't have R4 there, and it's not less or equal to 3, so we move on. Oh wait, k. Actually, I think I got it. You have to say, oh wait, yeah, no. This is right. This is right. Yeah. Sorry, nothing. Let's move on. Else condition, k. K is indeed in the keys. So now let's take a look at k minus 1. Is k minus 1 in the keys? It is. So we're going to use this. We're going to take a look at, these things. dk, d4, I think it does have a value of 8, yeah. And then dk minus 1, d3, it does have a value of 3, so that's fine. We're going to look into these remaining reward functions. Now k equal to 3. K equal to 3, we go directly into this in R2, self R2, and that is a value that is not none, which is great. Okay, so now we also took a look at k equal to 2, so now we're going to use what? R1, which also is a legit value. And so now we have stored our k, we have stored into R a new value. Let's take a look. We have an R4. Huh. Okay. We have an R4, but we don't have an R3 yet. That's fine, I believe. So now let's go on. Now we're looking at k equal to 8, and we're in here. Do we step into again? K equals to 10. Step into again. Well, you don't really return it, right? Because our reward list only has here 1, 1, 4, and it's jumping a few things, you see? So somehow we have skipped calculating some values and decided to return an incomplete computation. I think that's where the problem is. And it's going to give you that none type warning or error. So now we more or less know where the problem is. Let's take a closer look at what we have here. So for the reward, right? If the number k, according to our logic here, if we already have the value stored inside the R list, we will directly just look it up. Otherwise, We see if it's inside the dictionary. If it is, we continue with the dynamic programming recursive calculation. If it's not in the dictionary, that means if it's not in the dictionary, that means what does that mean? That means we don't have that value in our original list of numbers. So the reward function of this k is equivalent to the reward function of k minus 1, right? Because including this value or not doesn't really matter because it doesn't exist in the list. So yeah, I think that makes sense, right? Say if we don't have like a 6 in our list, then reward 6 should be equal to reward 5 because you know what? Because there's no value 6 there. Right. So let's say this is correct. And oh, we should actually return. Right. I think that is what's missing. We should return this value instead of going into it. Yeah. Right. Okay. That's what's missing. You need to always return something. Right. Yeah, this really got me, guys. Right, it's now 37. I don't know if the answer is correct, but we'll definitely just send it to Leetcode for valuation. At this point, I'm not going to hand calculate everything. Okay, there's still some runtime error for a special case when there's only one element. Maybe it's just a special case. Okay, so what are we expecting if we only have um, a value of 1, right? So if we only have like a 1 here, we of course expect it to return 1. But I guess it'll give me error because what? Because we will have an assignment of index out of range. Yeah, I guess. So if we only have one element in nums, then yeah, because you see, when we initialize that, uh, we already did that. Okay, right. So yeah, so if we right, so what if you only have like a value of 1 there, or like if there's only one, if the maximum number you can have in the list, excuse me, is 1, then this list, we only just have one value, right? I mean, it could be the case. And it's for the reward, right? So we only do that if max is greater than 1. And we only do that if max is greater than 2. Right, right. Yeah. So there's a lot of things that we learned today. Have to, take care of these special cases, run code, run test cases. Why does it take that long? Submit the code. Finally accepted, but yeah, the performance sucks. All right, let's submit it again, see if it gets a little better. No, the runtime is really, really slow. So memory usage still below average. Well, I think we definitely need to learn more about how we can improve this code here because we're not on par with the average submission in today's implementation. Um, but let's just lastly, before we close today's um, coding, let's take a look at the solution. Well, yeah, well, it's definitely much faster than mine, but takes a bit more memory. Let's try it again. Yeah, it's an average speed, but the memory sucks. Ours were even worse. It took 3 seconds to run, and there's definitely a lot more that we need to optimize in our solution. We just barely made it work, but in terms of performance, it was really bad. So, but we're running out of time today, so I will stop here, and um, in some of those days, we will revisit this problem just to, keep up with my promise that we will submit a above average code each time. Um, but this time, today we're not doing it. So for today's summary, what I can say is that it's hell of a journey. Um, we looked at the problem of delete and learn and realized that, the first step of generalizing the problem was really, really hard for me to try to generalize this into, sub problems, into ways that we can wrap this in a dynamic programming solution. Um, we had a few first attempts, and actually most of our thoughts were aligned with the approach one in the solutions, but we just didn't quite get there. Like we didn't quite get the trick of using, um, after the transformation into a hash table, into a hash map or a dictionary, we didn't didn't take the trick of, uh, starting at one of the edges. In this case, we start at the largest number and then uh, we calculate our way down. Because by using the largest number, we can represent a subproblem by identifying, the largest number used, uh, the largest integer used in the original array. Um, so that is a way to represent, um, you know, that is a way to represent a subproblem, saying that we're only taking a subset of the original elements in the nums list that are between the elements that are between 1 and a maximum integer number. Um, and so that is the trick that we were missing. But after looking at the solution, we immediately caught up with that and then implemented this generalized recursive relationship. And we implemented this recursive relationship here. Uh, During that, we've um, we got ourselves into trouble by accidentally using global variables to store our pre-calculation results. And that was a bad idea because what I wasn't aware was that if I put my definition here, like between the class definition and, outside of any class member functions, it's going to be like a global variable that is shared not only um, among the member functions here, but among actually all instances of class objects defined this way and created this way. So that really made a mess, and I realized that. So to correct that, I initialized, you know, D and R inside class member functions, and that solved the problem immediately. But then um, this way of um, top-down calculating reward functions, um, it is not the fastest. Indeed, in fact, it was very slow actually. It turned out that we are at the bottom 10% in terms of speed performance for this code challenge. Um, so, but I'm not complaining. Other than the time that it took us to finally get there, I'm not complaining. This is progress. And last but not least is that we need to be careful about the special cases when there are only like one element or two elements, um, and you need to build something uh, to treat those special cases because the most general cases doesn't necessarily fit the description of like the special cases. So there it is, guys. That's my summary for today's problem. Um, I know it's probably gonna be a super long video, like 3 hours or even more. But hey, at the end of the day, we solved the problem, and there's a lot of takeaways I'm going to write down in the description of this video. Uh, and I will make sure that I use timestamps so that you can actually skip those steps where I'm basically just making mistakes, and so you don't have to waste time watching those sections. All right, that wraps up today's episode. Thank you all for sticking along with me, and see you in the next video.